Hi there, welcome to Emotional Detection Based on Vital Signs by Kaiwen Bian and Xiang Yi.
So within our presentation, we have included introduction, experiment, analysis, results, conclusion, and our future plans.
Speaking about the purpose of this project, I was always wondering if there is a way to set a baseline for machines to actually determine human emotions. And of course, the traditional way of how humans determine their emotion wouldn't work on machines. It would definitely need a standard baseline to determine it. And this is when me and my partner came up with this project.
So our process that we have in mind of coming to our goal is to have raw data and then analyze it using equations and a process of deconvolution, and then to finally get the result. So we were thinking, if we can use sensors to create a system that captures a person's heart rate and electric conductivity, or the GSR signals, then we can determine their emotions by analyzing the return data. These pictures shows the process we use to collect the data. We have the participant wear the heart rate sports band on one hand and the GSR sensor on the other. Then we would have a computer in front of them playing the emotion stimulus video and then retrieve the signals.
And how we're collecting the data is by having the participants all signing an agreement sheet first, and then we're going to adjust both sensors, the GSR and the heart rate band, to a certain base levels, and then we're going to help the participants to wear these sensors to eventually we can retrieve the data from them. So these are the equations we have used to find a baseline from the raw data. The reason for a baseline is that we need these baselines to then test whether if the baseline can determine what emotion it is. And these equations come from a published South China University of Technology paper, and these equations can help separate our raw data into different categories of emotions. Here we have the results of the raw data. On the left side, we have the graph of the raw data of heart rates we use to set the baseline. And on the right is the trends of the raw data of the heart rates that we're going to use to test the baselines.
This is also a part of retrieving data's heart rate data, and this is basically essentially using BLE heart rate logger, the Bluetooth framework, to retrieve heart rate data from the band to transport it into the Raspberry Pi motherboard. And if we're gonna do later on AI recognition, it's gonna be a lot easier. And the way we are retrieving data is by accessing the notification handle and the heart rate handle of the BOM5 band. And then we have the Galvic skin response sensor, or other known as GSR sensor, and it's basically responsible for testing the conductivity of our participants' sweat glands and how much sweat it's releasing. Now the graph right here is basically showing the trend of raw data, and we can see how the variations of the GSR signals in one sample varies with time.
The following are the graphs of the 3 raw data sets we determine our baselines. So from these trends, we can see that the raw data all show a general trend. And therefore, because they all show a general trend, we can use them to determine the baseline, since they all have some similar characteristics. And in this case, it's that they have a similar trend in the different categories of the heart rate data. Here we have the different categories of heart rate data's baseline. So with these baselines, we can then use them to determine other raw data sets, and then to use them to determine what emotions the raw data are. On the right side, we have the overall accuracy of the baselines. So for example, when determining the emotion of happy, we have an 80% accuracy of determining it's happy. On the left side, we have the accuracy of the individual categories of data. It is worth to mention that we did neglect the positive or negative sign of our data, since it means the magnitude.
And then we have the GSR processes, in which we receive from our GSR sensor. So the raw data we receive from our GSR sensor will be processed by this human resistance equation that we
got from the Seed's official website. And using this equation, we can eventually convert our data into conductivity, which is a crucial data we need later on for a phasic analysis. And the graph right here is showing the data of the conductivity. Moving away from the primary analysis, now we enter the secondary GSR analysis, which is the deconvolution. And deconvolution is essentially making smooth signals more curved and outlining their peaks and changed in lines. And the main function that we're performing deconvolution on is the Bateman equation, which essentially is an equation stating the relationship between the sweat glands conductivity and the sweat released. And basically after performing deconvolution, we will receive the tonic data and the impulses, and from using the tonic data we can eventually get the phasic data, which is crucial in determining the emotional arousal. And now we have the phasic deconvolution part, and from the third row we can see that's the phasic activity of our samples. And as we said about deconvolution before, we can see how it's curved and how we can find out the emotional arousal and changes in it. So now we have the analysis results of GSR's emotional arousal. So the emotional arousal of the phasic data is defined as when there's a curve or a big change in the phasic line. And we can see from the sample right here at 10 seconds, there is a change in the line, which means that there is an emotional arousal happening right here. And from our samples, data from the bottom and the graphs on the bottom, we can see that all test subjects all have been through at least one time of emotional arousal throughout the emotional stimulus video. So the overall results, as we can see from the previous slide, the phasic data we have all participants going through emotional arousal while watching the emotional stimulus video, which means that we have 100% accuracy on that. And for more specific characterization using heart rates data, we have 80% accuracy for happy, 30% for angry, and 43% for sad, which means that happy, whether it's going to be the simplest emotion to reveal or there are some fallacies in our system that's not making our participants angry or sad enough to be tested out.
So the benefits of this project is shown in two areas: societal and scientifical. So societal, we can use this technology to help different platforms or any applications to determine its users' emotions, and thereby having a much more usage of this determination. And as for scientifical, this method can be used to train AI algorithms and therefore being more developed.
Overall, we have used a heart rate band, so retrieving heart rate data, and GSR signals to determine emotion. Thereby, we can then analyze the raw data with equations and deconvolution to then eventually determine whether if there is an emotion change and then what type of change, so what kind of emotion it is.
So some areas we can do better on is, first of all, definitely a longer emotional video to test out all the emotions the participant had. And then we can also have a more sophisticated analysis to reduce some sorts of errors in calculation.
Some improvements would be to have a larger sample size to increase our accuracy, and to have a better test area, a testing environment, so that the participants can actually have the emotion, and also to upgrade our hardwares.
So for future plans, we are planning to use AI algorithms like the TensorFlow ones, and to basically make a full automatic machines that can test out the emotion and analyze it. And also we plan to add more sensors like the re-speaker, voice recognition, or facial recognition, etc., to improve the accuracy of the data. And here is some reference of the sources that we have used. And this is it. Thank you guys for watching this video.